That's ethane. If I gave you a problem, an empirical formula problem, describing this, and I said it's a certain percent of carbon, it's a certain percentage of hydrogen, what is the formula for this compound? When you use the process of converting to moles and dividing all of them by the lowest number of moles, you know what I'm talking about, right? How to find empirical formula? You divide all of them by the lowest number of moles, it gives you the mole ratio. The empirical formula process would give you CH3 as the formula for ethane, because this is the lowest ratio. But we know ethane. We know ethane's structure looks like that. That is not CH3, it's C2H6. Every molecule is the same, C2H6. How do we go from this, when we use our empirical formula process, to this, the actual correct formula of the substance? Well, that's what molecular formula. This would be considered the molecular formula, and that's what the actual formula of the compound is. But this is the lowest ratio of elements to one another. The way we do it, and that's what this paragraph tells us, the molar mass of CH3 is 15. Because carbon's 12 and hydrogen's 1, and there's 3 of them. So this has a mass of 15. If you add them up for ethane, the molar mass is 30. 12 times 2 is 24, plus 6 is 30. Notice that the molar mass of ethane is twice as much as the molar mass of its empirical formula. It's exactly twice as much. And this is the way that molecular formula is always going to work. You're going to be given this. You'll be given that in the problem, the molar mass of the molecular formula. So what you're going to do is you go through all the steps, find the empirical formula, but then that last step, you're going to figure out what the molar mass of the empirical formula is and see how many times it goes into the molecular formula's mass. And that will be a whole number. Like in this case, it was 2. 15 goes into 32 times. Therefore, you take this formula and multiply it by 2, or through by 2, and you get the actual formula of the compound. So we'll just have to do this. You'll be given that. That little green star there tells us you're going to be given that number so that you can figure out what the actual formula of the compound is. So I have a problem that I'd like you to try. And what do we have? 15 minutes or so left. We'll need all that 15 minutes. It's a nasty one. You ready? It's the end of the day. At the end of the week. You got this? You can't say no, because
I always love when they say you're what are they going to say?
That's true. I want to give you a couple minutes just to wrestle with this, and then we'll talk a little bit. Stop.
There's a flash of
Could you write a chemical equation for this reaction? reaction. It's a reaction, right? It tells what kind of reaction. Combustion, see that? And we know the general form of a combustion reaction. We have a hydrocarbon. We don't know what it is. We just know there's C and H in it. So I'm going to write the formula like this. Just because I'm going to guess that X and Y are not the same thing. They might be. But it's going to be that some hydrocarbon and any other reactant. Oxygen. There has to be oxygen. It's not going to be combustion unless it's oxygen. And what are the products? And? Yeah, CO2 and water. Right. Okay, so we have a chemical equation for this thing. It's not balanced, of course, because we don't know what this is. And it doesn't really help us to balance, you're going to find out. And that may be a little bit weird because you think, well, we can't do this unless the equation's balanced. In this case, you can. But this is nothing like we would have done in Chem 1. I'm going to go ahead and write in to the chemical equation what quantities we're given. We're given the fact that 17.6 grams of CO2 gas got made. So I'm going to write that in there. 17.6 grams of that got made. And then the water, 9 grams of water got made. How does that help us? We want to figure out what this compound is. What is its formula? See if that helps. Feel free to talk to one another too. Talking to one another doesn't mean getting up out of your seat and going to talk to Reed. I'm not going to mention any names.
Anyone else is smart in this class, now's the time to volunteer.
You're all super smart. You know that. I know that.
My brain capacity is far inferior to yours, and I would like to get a glimmer into the stream of consciousness.
You got it? Don't say it out loud.
I got it.
Don't you remember?
Stop lying.
Colby knows it.
Don't know how to get to it.
Too long.
I just remember, I don't know how to do it. I just remember.
We're going to get there, though. You'll see how to do it. Okay, I want to give you a boost. Are you ready for a boost? You need to work for a minute. No, okay. So we know how much products are made. How does that help us to know how much reactant? Well, I want you to check this out. I see carbon in this reactant. There's carbon. Is there any other carbon in the reactants besides what is right here? No. Okay, look over at the products. I see carbon here, and I know how much of that was made. There's no other carbon in the products. So all the carbon that was in here wrapped up in this compound is now all wrapped up in that compound. Now, if I know that there were 17.6 grams of this made, can I convert that to moles of CO2? Yes, it's a simple mole conversion. If I know how many moles of CO2 there were, do I know how many moles of carbon atoms were made? Yes. In fact, it's the same. However many moles of CO2 there are, that's how many moles of carbon there were. So that'll tell me how many moles of carbon there are at the end. That's exactly how many moles of carbon there were at the beginning. Same thing with hydrogen. I see hydrogen only right there in this compound. Over here, I see hydrogen only in this compound. So if I know how many grams of water were made, I can do a mole conversion, see how many moles of water were made. And if I know moles of water over here, I'd be able to figure out how many atoms of water, or how many moles of I said that wrong. I said atoms of water, that's wrong. If I know how many moles of water, I can figure out how many moles of hydrogen there were. Do that. Take these values, convert them to moles of carbon into moles of hydrogen. There's at least one, and maybe two, combustion problems like this in the exercises at the end of the chapter. So you'll have more practice doing problems like this. And there's more problems like the hemoglobin problems. If you'll take a look, time is running out here in class. Take a look at what I did up here. Is that the direction that you went on your paper? You went from the mass of CO2 converted to moles of CO2. That's what we do right here. And then from moles of CO2, every mole has one carbon in it, so it's a 1-to-1 ratio. So we know that there are 0.4 moles of carbon in that mass of CO2. So that means that this carbon right here, there must have been 0.4 moles to start with. Same thing for hydrogen. We had started with 9 grams of water. We converted that to moles. It's a half a mole of water, 9 divided by 18. But then every water molecule has 2 hydrogens in it. Be careful of that. Don't assume that the moles of the compound are the same as every element in there. There's 2 H's in every one molecule. So 2 moles of hydrogen atoms in every 1 mole of water. That means that as there were 0.4 moles of carbon, there was 1.0 moles of hydrogen that we started with in this compound. Now, if we know how many moles of carbon there were and moles of hydrogen, can we find the empirical formula for this thing? We'll learn how to do empirical formula. That's what I had, but I forgot to erase at the beginning of the hour today. 0.4 moles of C and 1.0 moles of hydrogen. To find the empirical formula, we do what with these numbers of moles? Divide by the lower number of moles. Yep. So that divided by itself is going to be 1. And that divided by 0.4, I just said 0.04, didn't I? Anyway, That's 2.5. 1 divided by 0.4 is